Rightio, so last time we met the concept that if we took the pressure of a gas and we plotted on this side the temperature in Kelvin, and this bit is important, but it's in Kelvin, we get a straight line through the origin. We get this lovely thing that for a, and this leads to what we call the pressure law, which states that for a fixed mass of a gas at a constant volume, the pressure is directly proportional to the temperature in Kelvin. That is what the pressure law sort of states in words. Now, I did in the video, I talked about, like, it was called, some places called the Gay-Lussac law. I did actually discover why it doesn't get that name generally. It turns out it's because actually there's about 3 people who all really stumble across it in the same way. Dalton and Antinous or something. Antinous. There's like 3 of them, and all around about the same time, they all basically set out the same law in slightly different ways of wording it. And so it just overall gets known as the pressure law because, the things you learn. Now, we can use this, much like with the Boyle's law, we can use this to solve a problem. We can try and think, okay, if we change something, if we change the temperature, then what can happen to the pressure? So let's take how we deal with this. What this tells us, okay, is that the pressure is directly proportional to the temperature, okay, measured in Kelvin. And if we do our little, if we do our mathematics again, that would allow us to say that pressure of the gas is equal to some constant times the temperature. Okay, we did see this at the end of the last lesson, where that actually what it means is that if you take the pressure and you divide it by the temperature, we get a constant value. And much like Boyle's law, the number you get is going to depend on the volume of that container and the size and the number of amount of gas and stuff that's in there. But what it gives us is this relationship where the pressure of this gas divided by the temperature of the gas in Kelvin is going to give us a fixed value. So we can see that if we took, let's say we took a normal kind of, let's say we took a sort of sample of gas and we had at a temperature, let's say we have at a temperature of, say, 298 Kelvin, which is essentially 25 degrees Celsius, and we have a pressure of 101 kilopascals, what would this constant value be? Well, annoyingly, I should really have done it the other way. So let's just take this and move that up there. Let's move that way down. So let's make that a bit nicer. So we could say, okay, so what happens with either pressure over temperature? Well, that's going to equal 101 kilopascals over 298. I'm not going to bother. Do 101 over 298, and I get 0.34. Okay, so that comes out as being 0.3389. So I'm going to go 0.34. Okay, that's our constant. Well, we can ask ourselves a question of, okay, well, what would happen if, let's say, we doubled this temperature? let's say we double the temperature, what happens? Okay, so we can say, okay, what happens? Okay, what happens if we double the temperature? Now, importantly, okay, because pressure is proportional to temperature, we're going to expect if temperature goes up, temperature increases, then pressure must also increase. So, you know, we can see what happens. You might be able to predict what happens. You might be able to predict a number that you might get, but let's see what we get. So what we'd say is that we would now be in a situation where we'd have to say, oh, okay, so 0.34 is now equal to our new unknown pressure over what is now double this, so 298 times 2, which is 596. Because if this law is true, then, you know, then this ratio of our initial pressure and temperature should be equal to the ratio of our final ones. So this allows us to say that our new pressure is going to equal 0.34 times 596. So, and lo and behold, we get 202 kilopascals. Okay, if you type in exactly 0.34, you're going to get a slightly different number because this is 0.3389 or something. So it comes up, but then we get 202. Oh look, we've doubled the pressure. We doubled the temperature. That led to a doubling in the pressure that is being exerted, and this gives us the pressure law. What we can do is that, given that we know that our initial pressure divided by our initial temperature is equal to a constant, which must therefore equal our final pressure divided by our final temperature. Well, this constant isn't really important. We don't really need it, so we can just remove it. So pull it out. Let's shove it over there. And we can say, okay, well, there we go. And that right there, that is mathematically how it allows us to use the pressure law. It allows us to see what is going to happen to the pressure if we change, as we change the temperature. Okay, our ratio of our first pressure to temperature will equal the ratio of our final pressure to temperature. And so now this is very similar to Boyle's law. If you remember Boyle's law, it's just sort of Boyle's law was pressure 1 times volume 1 is equal to P2 V2. So it's a similar kind of property. Okay, it's just, you know, slightly mathematically they're divided rather than multiplied together to get the same thing. But we can use it in the same way. What we'll get is we'll know 3 of these, and it allows us to work out the 4th one that we're missing. Now the trick, however, is always remembering that these temperatures, okay, is, remember, the temperature must be in Kelvin. Okay, they cannot be in degrees Celsius. And this often would turn this kind of question into being a bit more, you know, tricky than this one, mostly because it would require you to do a conversion from Celsius to Kelvin and then back again. Okay, so let's do a sort of an example of just how they could do this. So let's give a sort of as an example. And this is kind of as involved as it can be. A gas at a pressure of, let's go with 125 kilopascals is at an initial temperature of, let's say, 35 degrees C. What is the new pressure? When the temperature increases to 70 degrees C. Okay. Now, this initially, you might think, oh, look, the temperature, it's just doubled. But it's only doubled in cases of degree C. That isn't the same as doubling temperature. These two temperatures cannot be used in the equation. They will give us the wrong answer. So what we need to do is we need to say, okay, what we first need to do is step one is convert to Kelvin. Now, if you remember Kelvin, that basically means you're going from Celsius to Kelvin. You've got to add 273 to each number. Now let's label these up. This is T1 and this is P1. This is T2. So we now know is we want to say that T1 is equal to 35 plus 273. So that's going to equal 308. And T2 is equal to 70 plus 273. Annoying. 273. So that is equal to 303. Okay, so these are our temperatures to use in the equation, not these two. So now we're in a position to use the pressure law. Okay, and that means that we've got we're going to use P1 over T1 is equal to P2 T2. We can insert our numbers, so we've got pressure 1 is 125, so that gives us 125 over our initial temperature, which is 308, is equal to our second pressure, which we don't know, over 343. So we've got 125 divided by 308 is equal to something divided by 343. And what we can do is we can do this with the cross multiplication, and that will bring this up to there. So that will become 125 over 308 multiplied by 343 is equal to our new pressure. We multiply that up, 125 times 343 over 308, we get 139 kilopascals. Now the unit, kilopascals, because we're dealing with ratios, the unit of this thing is going to be the same as the unit that we had there. So you don't need to worry really about what unit they give you here. Because it's a ratio, whatever unit your pressure will be, you're going to get the same unit on the other side. So that's very fun. So that's kind of one example. Let's say they wanted to make it a little bit trickier. Let's deal with the second example. Okay. Let's say we've got a gas at a pressure of, let's say we've got 84 kilopascals is at an initial temperature of, let's say we've cooled this down to minus 7 degrees Celsius. It is heated and the pressure rises to, let's say, 108 kilopascals, what is the new temperature in Celsius? Now, just so you're aware, this question, a question that was like this, would have always carried 4 marks. Every single time would have been worth 4 marks. And the way to only get 2 of that is to fail to come out of Celsius. Okay, so what we're dealing with this time is we now need to say, oh, we're trying to work out the temperature at the end, but we've got that conversion in it as well. So let's deal with the end of it. Didn't need to. So let's say we've got, let's label things up always. So that's our pressure 1, that's our temperature 1, and this is our secondary pressure. But we need to convert that into Kelvin. So T1 is going to equal, you know what I'm going to do just to sort of make it a bit easier. I'm going to hold this, I'm going to do the second in red. So our first temperature is got to go into Kelvin, so we've got to add 273. So we've got -7 plus 273, which is 266 Kelvin. Okay, and now we're in a position to put this in. So we want, so we'll have 84 over 266. Okay, so we've got P1 over T1, and that's going to equal our secondary pressure, which we now know is 108 over T2. We don't know what T2 is. Okay, so that equals, so that's P2 over T2. But again, we have a nice thing. We're just trying to find out this one. So what we have is, you know, you can either sort of work this bit out and say, well, what is 84 over 266? That's 6 over 19, or 0.316. So this ratio comes out as being, so 0.316 is equal to 108 over this second temperature. To sort this out, we've got to multiply up by that. I'm going to divide through there. So that becomes, so T2 is equal to 108 over 0.316. So 108 over that after, and we get, oh, we've got 342 Kelvin. So we've got a temperature. Have we answered the question? No, because it wants us to give it to us in Celsius. So we say, okay, so to convert to Celsius, we subtract 273 from our answer, 3 minus 273, and we've got 69 degrees C. So T2 is equal to 342 minus 273, 69 degrees Celsius. And that is the sort of like the answer that we get, 69 degrees Celsius. If we have a kind of, if you forget to do the conversions, you're going to end up with a particularly, you're not going to end up with a particularly helpful number. Let's just see if we do this. Let's do this wrong just briefly and see what we end up with. What you end up with, if we forget to do any conversions, you'd end up with 84 over -7 is equal to 108 over sort of like a question mark. And this is where this becomes a problem, because this is now a negative number. And this is therefore going to make very little sense at all. 84 over -7 is -12. So we've got -12 is equal to 108 over a question mark. So you've got our new temperature is 108 over minus 12, and you end up with minus 9, which makes little sense because you think about it. What that means is that our pressure has gone up, but our temperature has for some reason gone down. So this is why working in Celsius won't work. This is a silly answer. And it's so silly, in fact, I don't want it to be on the whiteboard. So delete it. Because no one therefore will ever know that we did it. But that's how we use the pressure law. And so, yeah, it's time to use that and try and do a bit of practice in using it. Works exactly the same if you're trying to deal with, if you're trying to find, whether you're trying to find a new pressure or a new temperature. This is how we approach it.